Hello, everyone. Let me begin today's session with a question. Have you ever wondered why a diamond is so rigid that it can cut through glass, while a simple piece of plastic bends so easily? The secret lies in the fascinating world of solids. As you already know, matter exists in three states: solid, liquid, and gaseous. But solids stand apart because their particles, whether atoms, ions, or molecules, are packed so closely that they hardly move. This tight arrangement gives solids their definite shape, high density, and incompressibility. We broadly classify them into crystalline solids, which have long range order, and amorphous solids, which have only short range order. For example, ice and sodium chloride are crystalline, while glass and plastics are amorphous. Let's dive deeper into what makes these two categories so different.
Now, let's take a closer look at crystalline solids. Imagine arranging rows of chairs in a perfectly repeating grid for a school assembly. That's exactly how particles are arranged in a crystalline lattice. These solids have a definite geometrical shape and a sharp melting point because the entire structure breaks down at once when sufficient heat is supplied. One remarkable feature of crystalline solids is anisotropy. Their properties, such as refractive index and electrical conductivity, change depending on the direction in which they are measured. Cut a sodium chloride crystal, and you will notice it cleaves neatly along flat surfaces, producing smooth, clean edges. Famous examples of crystalline solids include sodium chloride, diamond, quartz, and metals like copper. They are nature's perfect architects, showcasing beauty in order and symmetry. Now contrast this with amorphous solids. Picture a jar filled with marbles shaken randomly. There's no repeating pattern, just a short-range order. That's how particles are packed inside glass, plastics, and rubber. Amorphous solids do not melt sharply. Instead, they soften gradually over a range of temperatures, which is why glass blowers can mold glass into beautiful shapes. Unlike crystalline solids, amorphous solids are isotropic, meaning their properties, such as conductivity or optical behavior, remain the same in all directions. And when broken, they don't split cleanly, but rather produce irregular, curved fragments. Everyday objects like window glass, rubber bands, and plastic bottles are excellent examples of amorphous solids. These are often called supercooled liquids because their structures resemble that of a frozen liquid. Let's now compare crystalline and amorphous solids head to head. In crystalline solids, the arrangement of particles is highly regular and extends throughout the structure, while in amorphous solids, the arrangement is irregular. Crystalline solids have a sharp melting point. Sodium chloride, for instance, melts sharply at 801 degrees Celsius. Amorphous solids, however, soften over a temperature range. Cleavage is another key difference. Crystals like diamond or sodium chloride split neatly along definite planes, whereas amorphous solids like glass break into irregular, curved fragments. And finally, crystalline solids are anisotropic, meaning their properties depend on direction, while amorphous solids are isotropic, behaving the same in every direction. Think of it this way: diamond is a crystalline solid, glass is amorphous, and that explains why one cuts while the other shatters unpredictably. Crystalline solids themselves can be grouped into four major categories, depending on the type of forces that hold their particles together. The first type is molecular solids. These are held by weak van der Waals forces or hydrogen bonds, which is why they are soft and have low melting points. Dry ice, which is solid carbon dioxide, is a perfect example. The second type is ionic solids, where strong electrostatic forces bind positive and negative ions. Sodium chloride and magnesium oxide fall under this category, and they are hard, brittle, and have high melting points. The third category is covalent or network solids, where atoms are linked by a continuous network of covalent bonds. Diamond and quartz are classic examples, extremely hard and often used in cutting tools. The fourth category is metallic solids, where positive metal ions are surrounded by a sea of delocalized electrons. This electron cloud explains why metals like copper, iron, and aluminium are such good conductors of heat and electricity. Each of these types is unique in its bonding, structure, and properties, making crystalline solids an incredibly diverse class of materials. One of the most fascinating differences between solids is isotropy and anisotropy. Crystalline solids are anisotropic, which means their physical properties, like electrical conductivity or refractive index, vary with direction. This happens because of their highly ordered arrangement of particles. On the other hand, amorphous solids are isotropic, showing identical properties in every direction due to their irregular packing. For example, quartz crystals bend light differently depending on the orientation, which is a property used in polarizing filters and in liquid crystal displays. Glass, however, being amorphous, does not show such directional dependence. This concept of anisotropy versus isotropy not only helps us understand the behavior of solids but also finds applications in optics and electronics. So let's quickly recap what we've learned today. Solids are broadly divided into crystalline and amorphous types. Crystalline solids are characterized by long-range order, sharp melting points, anisotropy, and clean cleavage. Amorphous solids, in contrast, display short-range order, gradual softening, isotropy, and irregular breakage. Within crystalline solids, we identified four major categories: molecular, ionic, covalent, and metallic, each with distinct bonding and properties. From the hardness of diamond to the malleability of copper, and from the brittleness of glass to the transparency of quartz, the classification of solids explains it all. I hope this session has helped you see solids not just as rigid objects, but as fascinating chemical architectures that define our materials, tools, and even technologies. Catch you in the next class, where we'll explore the magical world of crystal lattices and unit cells.